Hello friends, it's a beautiful morning in Kigali and I hope you are doing great. IBM is here with another episode of Learning Physics and this is specifically solve the past paper questions that we are going to be looking at. Do not forget to share these videos with your friends, your classmates. It's better you download the document under the video description so that you can always follow from a hard copy when printed. It is easier to learn in a hard copy when you try to work out on the question paper. So it's better you print the document in the video description. You can even print per copy per topic so that you follow topic by topic as you prepare for your AS A-level exams. This will be very important. So this is kinematics and I think this is part 3. I don't know whether it will be the last part, but perhaps it is one of the last parts, if not the last. So this is kinematics, solve the past paper questions, and this is going to be part 3 of these videos. Without wasting any time, I would like to let you know that in kinematics, we are supposed to discuss questions involving velocity, speed, acceleration, distance, and displacement. We shall describe motion many times, use equations of motion, look at projectiles, and a lot more. So do not miss these topics, do not miss the discussion in these solve the past paper questions. Without wasting time, I would like to take you to the document so that we pick up from where we stopped in part 2. So let's move to the document. So this is the document, and I think we stopped on page 94, I guess. We stopped on page 94. And we are going to start from there. A ball is thrown horizontally from the top of a building as shown in the figure. The ball is thrown with a horizontal speed of 8.2 meters per second. The side of the building is vertical. At the point P on the path of the ball is a distance x from the building and is moving at an angle of 60 degrees to the horizontal. Air resistance is negligible, meaning we can employ the equations of motion because there will be uniform acceleration. For the ball at point P, show that the vertical component of its velocity is 14.2. Before we go any further, let's draw the two perpendicular lines here for the velocity vertically downwards, and for the horizontal velocity, I'll draw a horizontal line. So of course the resultant velocity is the one which in the direction of motion, that is the resultant. So we want to find the vertical velocity. Of course, velocity in the horizontal does not change. It remains 8.2 meters per second. Why? Acceleration in the horizontal is always 0 because there is no force acting in the horizontal. But if we resolve this velocity in the horizontal, let me call this V. Resolving V in the horizontal gives us V. This angle here is also 60 degrees, just like the other one. If we resolve V in the horizontal, it gives us V cos of 60. If we resolve V in the vertical, therefore it will give us V sine of 60. So having resolved, now we can look at the question. So that the vertical component of its velocity is 14.2 meters per second. So we have seen that in the horizontal, we have seen that V or 8.2, which is the horizontal velocity, is equal to V cos of 60. Then the vertical velocity, I'll call it V in the y, I'll call it Vy, is going to be equal to V sine 60. So we want to find Vy. So what we shall do, we shall just divide Vy by Vx, that is Vy divided by 8.2 should be equal to V sine 60 divided by V cos 60. So V cancels out. So it means sine 60 over cos 60 is tan. So we can see that the vertical velocity Vy is going to be equal to tan. It will be 8.2 tan of 60. because sine 60 over cos 60, that is tan 60. So we can substitute, press the calculator, 8.2 tan of 60, which gives us 14.2. So this is equal to 14.2 meters per second. Okay. Determine the vertical distance through which the ball has fallen. Vertical distance through which the ball has fallen. In other words, we want the distance from the point of projection to point P in the vertical. So since it was initially moving horizontally, if I consider vertical motion, it means initial velocity in the vertical is 0. So I will use v squared equals to u squared plus 2as. Velocity at P in the vertical is 14.4. So I will say 14.4. I'm considering vertical motion. I can put y here. Velocity at P is 14.2. Now this is squared. Initial velocity in the vertical is 0. Plus, because it's falling downwards, we shall not put a minus there. 2 times 9.81, that is acceleration due to gravity, then times the height h, or the vertical distance h. So it means h is going to be 14.2 squared divided by 2 times 9.81. So this would be 14.2 squared divided by 2 times 9.81. So that gives us 10.3 or 10.277 or 10.3. So that distance is 10.3 in meters. Then determine the horizontal distance x. So we want to determine x, so we shall consider horizontal motion for horizontal distance. So s in the horizontal is equal to initial velocity in the horizontal times t, then plus a half acceleration in the horizontal times t squared. Of course, I can't put x on t because time is the same, time is a scalar quantity. But for horizontal motion, I'm considering displacement in the horizontal, initial velocity in the horizontal, acceleration in the horizontal. And I want you to always remember that acceleration in the horizontal is always 0 because there is no force in the horizontal. The only force acting here is the force due to gravity, which acts in the vertical direction. So therefore, it means the displacement, the horizontal distance x that we want will be initial velocity in the horizontal, which is 8.2 times the time t. So we need to find t. T is the same whether you consider vertical motion or horizontal motion. So let me find t. I will use v in the vertical equals to initial velocity in the vertical plus acceleration in the vertical times t to find time t. V in the vertical, we have it above as 14.2. Initial velocity in the vertical was 0 because the body was projected horizontally. Then plus 9.81, then times t. So it means t is equal to 14.2 divided by 9.81. So it means now I will find x as 8.2 times 14.2 divided by 9.81. So that is going to be 8.2 times 14.2 divided by 9.81. So that gives us 11.87 or 11.9. So the displacement, the horizontal distance x is 11.9 meters. The path of the ball in A with an initial horizontal speed 8.2 is shown again here. On the figure, sketch a new path of the ball for the ball, having an initial speed greater than 8.2 and with negligible air resistance. There is no air resistance and the speed is greater. That means it is going to fall further. It will hit the ground at a more acute angle. So it means the path will be now this side. So they said label this G. So this is G. When there is no air resistance and the speed is greater. Then the speed is equal to 8.2, but air resistance air resistance, but with air resistance. If the speed is the same as 8.2 but there is air resistance, then the ball will fall closer to the wall. The ball hits the ground at a steeper angle. So this will fall, this will be somewhere here, closer to the wall. So this one, they said label this path A. Okay, so that is it. Next, a ball is thrown from a point P, which is at a ground level, as shown in the figure. The initial velocity of the ball is 12.4 meters per second. Initial velocity is 12.4 meters per second, so I'll make this to be 12.4 meters per second. When we resolve it in the horizontal, it will be 12.4 cos 36, not 60. Cos 36. When we resolve it vertically upwards, to be 12.4 sine of 36 degrees. Okay, the ball just passes over a wall of height h. The ball reaches the wall 0.17 seconds after it has been thrown. Assuming air resistance to be negligible, meaning the equations of motion can apply because the acceleration is now constant. Calculate the horizontal distance of point P from the wall. Horizontal distance. For horizontal distance, I will consider horizontal motion, that is horizontal distance x, sx, initial velocity in the x times time t plus a half a in the x times t squared. Remember, if I consider horizontal motion, acceleration in the horizontal is 0. That means the horizontal distance sx is going to be initial velocity in the horizontal. I have to resolve 12 in the horizontal. So that would be 12.4 cos of 36 times the time. The time is 0.17. Remember, this other part becomes 0. This part here becomes 0. So we have 12.4 cos 36 then times 0.17. So that gives us 1.7. So that distance is 1.7. The height h of the wall, determine the height h of the wall. We want the height h of the wall. So height is in the vertical, so using the same formula, S is equal to ut plus a half at squared. I'll now consider vertical motion, S in the y, initial velocity in the y, acceleration in the y. So height S in the y is the height h. Initial velocity in the vertical, we resolved the speed in the vertical, so it is 12.4 sine of 36. Here I will put a minus because the body moved against gravity, so it will be minus. The acceleration will be negative. So minus a half times 9.81. Oh, there is a t here. The time, remember, is the same. So this is times t, which t is 0.17. Then minus a half times 9.81 times t, which is 0.17 and squared. The time is the same whether you consider vertical motion or horizontal motion. So we have 12.4 sine of 36 times 0.17 minus open brackets 0.5 for a half times 9.81 times 0.17 squared. So we are getting 1.097 or approximately 1.1 in meters. 1.1. The second ball is thrown from point P with the same velocity as the ball in A. For this ball, air resistance is not negligible. The ball hits the wall and rebounds. Air resistance is not negligible. It means it is going to move on a path. The path will actually be less than the one which is already there, because air resistance is not negligible. The number two, of course, if the path, if air resistance is not negligible, there is also a possibility of the graph becoming horizontal. Then on the figure, by the way, it rebounds. On the figure, sketch the path of this ball between point P and the point where it first hits the ground. Okay, so we are back here. The speed is the same as 12.4, but there's air resistance. That means the new graph will be below the one which is already there. So I'll drag graph inwards, I'll increase the thickness. So I'll drag graph which is inwards. So that is when it reaches the wall. Then it rebounds. When it rebounds, because still there is air resistance, so since it rebounds, then it will fall backwards. It will fall back to, because still there is air resistance, it will not fall, it will not go beyond the point of projection. So that is, this is going towards the wall, and this is rebounding. It rebounds. You see this part here is almost the same when it rebounds. So it rebounds and falls back towards the ground. Okay. So that is the sketch I expect a serious student to draw. It is a smooth curve with the ball hitting the wall just below the other one, the original point, and the rebound should be short. Because there is air resistance, the ball will not fall back to the or beyond the point of projection, so it falls within. Okay. A student makes or takes measurements to determine. A student takes measurements to determine a value for the acceleration of free fall. Some of the apparatus used is shown here. So this is an electromagnet. So the ball is going to start with initial velocity 0. They have given us corresponding values of t squared and d in the graph. So here we have values of d against t squared. These are corresponding values. Then on the figure, draw the line of best fit for the points. Line of best fit. We have points. The points that we have 1, 2, 3, 4, 5. Okay. So using your ruler, you can draw the line of best fit through these points. So I'm putting here my ruler. I hope I try to be very accurate, which is not easy with a computer. Okay, I hope I've tried my level best. You can draw a better line of best fit, but this line, I think it can go through all the points very accurately. The line can go through all these points very accurately. So that will draw a better line of best fit than mine. Mine is not very easy because it is by computer, but I can try. Okay, so I have tried. You can draw a better one. You can draw a better one, better than mine. Yeah, I'm trying my level best to draw a better line so that I have better results, but it's not very easy. Okay, let's go with that one. Let's try to go with that one. Okay, so draw the line of best fit. I've drawn the line of best fit, which is not easy. State and explain why there is a non-zero intercept on the graph. So we see that there is a non-zero intercept on the graph. The graph is not going to the origin. Of course, we are having a graph of d against time t. When we look at the diagram, you notice that d is not the distance fallen through by the ball. D is the distance which is equal to this height here, the distance fallen through, plus the diameter of the ball. D equals to distance fallen plus diameter of the ball. So it means D involves the diameter of the ball. It is not the distance fallen through. That's why the graph is not starting from the origin, so it is having a non-zero intercept. So we can say the distance fallen is not D. The distance fallen is not D, but D is the distance D is the distance fallen plus, or plus is single S. D is the distance fallen plus the diameter of the ball, plus the diameter of the ball. That's why we have a non-zero intercept. Or you would simply say D is not measured to the bottom of the ball. You would simply say that D is not measured to the bottom of the ball. D is not measured to the bottom of the ball. Determine the student's value for the diameter of the ball. Student's value for the diameter of the ball. Of course, you just look at the graph for the y-intercept. So the diameter of the ball. This is approximately in the center of this box. The scale is 10 divided by 10, 10 small squares. That is 1 unit, which is 1 centimeter. So this is 1.5. So the diameter of the ball is approximately 1.5 centimeters. Depending on how accurate your line of best fit will be, we can allow plus or minus 0.5 centimeters, meaning you could have your diameter as 1 centimeter or 2 centimeters, in that range, between 2 centimeters to 1 centimeter. But mine is approximately 1.5. Then determine the student's value for the acceleration. So it is a graph of d against t squared. So using the equation s is equal to ut plus a half at squared. Initial velocity was 0. So where there is s, I'm putting d is equal to a half. Where there is a, I'm putting g, then t squared. So it is a graph of d against t squared. So we see that the gradient is going to be a half g. So the gradient is equal to a half times g. And what is the gradient? Let's find the gradient. Our line is from maximum, from 60. So the vertical I'll have 60 minus 1.5. So I'll say 60 minus 1.5 on the vertical. Remember it is in centimeters, so I will say times 10 power negative 2 to change it to meters, divide by. On the x-axis, we have 0, 2. This value here is in the middle of this box. 1, 2, 3, 4, 5, 6, 7, 8 and a half. 1, 2, 3, 4, 5, 6, 7, 8 and a half. So it is somewhere there. And on the x-axis, each small square is 0.02 divided by 10. So it is 0.002. So this is this is 1.5. So this is times 1.5. 0.002 times 1.5 small squares. That is 3 times 10 power negative 3 plus 0.12. So that is 0.123. So this value here is 0.123. So I hope I counted well. 1, 2, 3, 4, 5, 6, 7, 8.5. 1, 2, 3, 4, 5, 6, 7, 8.5. Okay, so that is approximately 1.23. So that is 0.123, then minus 0. So this is going to give us 60 minus 1.5, 1.5 divided by 0.123, which gives us 60 minus 1.5 divided by 0.123, which gives us 4.75 times 10, 475. Remember it is times 10 power negative, okay, times 1 exponent negative 2, which is 4.776. So this is 4.76, is it? Yes, 4.76 recurring. Okay, then we find the value of G. So G is going to be 4.76 times 2 because it is a half G is the gradient. So we multiply the answer times 2 and that gives us 9.5. So G is 9.5. The student's acceleration is going to be 9.5. A ball is thrown against a vertical wall. The path of the ball is shown in the figure. So we see when it goes and rebounds. The ball is thrown from S with an initial velocity 15. We can resolve 15, remember, in the vertical, where it will be 15 sine 60. In the horizontal, where it will be 15 cos of 60. When you have that in mind, then projectiles are going to be easy. Air resistance negligible. We can use equations of motion. For the ball at S, calculate its horizontal component of velocity. So in other words, we resolve horizontally. So I'll call the horizontal component Vx. So Vx is going to be 15 cos of 60. 15 cos 60, that is 7.5. Then its vertical component of velocity. So I'll call it Vy, which is 15 sine of 60. So 15 sine 60, which is 12.99, which is approximately 13. The horizontal distance from S to the wall is 9.95. The ball hits the wall at P with a velocity that is at right angles to the wall. That means it has reached maximum height at point P. At point P, it is at maximum height because the velocity is at right angles to the wall. It has reached the highest point. The ball rebounds. That means there's a change in direction to a point F. That is 6.15 meters from the wall. Use your answer in A, or your answers in A to calculate the vertical height. So we shall use V squared equals to U squared plus 2AS. Since height is in the vertical, I'm considering vertical motion. At maximum height, V is 0, so this is 0 squared. Initial velocity in the vertical, we resolved it vertically, and we got it was 15 sine 60, which is 13. So 13 squared minus, because it is moving against gravity, 2 times 9.81 times the vertical height h. So h is going to be 13 squared divided by 2 times 9.81. 13 squared divided by 2 times 9.81. So that is 8.61. Show that the time taken for the ball to travel from S to P is 1.33. S to P. So we can use, since we know the horizontal distance, I think we can even use the horizontal distance, but we can still use the vertical distance. There is no problem. Remember, time is a scalar. Whether I use horizontal or vertical, the time is the same. So let me use vertical for simplicity. Velocity in the vertical is equal to initial velocity plus acceleration times t. So I'm considering vertical motion. At the highest point P, velocity is 0. Initial velocity in the vertical, we saw it was 15 sine, which was 13, minus acceleration is 9.81, then times t. So t is going to be 13 divided by 9.81. 13 divided by 9.81, which is 1.325. 1.325, which is approximately 1.33 seconds. Show that the velocity of the ball immediately after rebounding from the wall is about 4.6 meters per second. Velocity immediately rebounding from the wall is 4.6 meters per second. Now I want to take you back here. Note that when we try to find the distance here, the vertical distance through which the object falls is the same as before. That means it is going to take the same time to fall backwards if it starts from point P to point F. So it means the time to land is still going to be 1.33. We can even check. That the time to land is going to be 1.33. If we consider vertical height, we can still show that the time is the same. Therefore, since vertical height is the same, the vertical height is the same. Vertical height is the same. So the time to land, the time to land is again going to be equal to 1.33 seconds. If air resistance is negligible, the time which it is going to take to land is going to be 1.33 seconds. And if we use S, now we are in the horizontal. If you use S in the X, being equal to initial velocity in the X times T plus a half at squared. So the displacement in the X when it lands is 6.15. This should be equal to the initial velocity in the X, which is what we want to find when it is leaving the wall. That is, I'm calling it UX. Then times the time, which is 1.33. Remember, the other part will be 0 plus 0, since acceleration in the X is 0. So it means initial velocity in the X on rebounding is going to be 6.15 divided by 1.33. 6.15 divided by 1.33, and that is 4.62. So this is 4.62, which is approximately 4.6 meters per second. Okay, so that is the velocity with which it rebounds. The mass of the ball is 6.0. The mass of the ball is 60 times 10 power negative 3. Calculate the velocity. By the way, if you can't agree that the time is the same, you can even check. If you consider vertical motion and use V equals to U plus AT, when it rebounds, it is initially rebounding horizontal. That means initial velocity in the vertical is going to be 0. Initial velocity in the vertical is going to be 0. And you can find the velocity with which it lands. Alternatively, you could also think of S equals to UT plus a half AT squared in the vertical. And you want the time T. S is the vertical height, which we have already got as, I think the vertical height was 8.61. That was the vertical height, because it is going to fall from P back to F, the same vertical height. The initial velocity with which it rebounds is 0 in the vertical, if we consider vertical motion. So this will be 8.61 will be equal to a half times 9.81 times T squared. You can check and find T. The time it is going to take to arrive back, because it starts with 0 in the vertical. At rebounding, it rebounds initially horizontally. So initial velocity in the vertical, when it is rebounding, it is 0. So we have 8.61 times 2 divided by 9.81. Then we find the square root of the answer, which is the same as approximately 1.33, approximately. So it's only because this one, S in the Y, is rounded off, but time is going to be approximately the same, 1.33. It's only that S in the Y, or the height, we had already rounded it off. But if we use original values, it is going to be approximately the same, 1.33. Remember, I'm saying on rebounding, it rebounds initially horizontally, meaning that the initial velocity on rebounding is 0. Okay, I think that is fine. So the mass is given as 60 times 10 power negative 3. Calculate the change in momentum of the ball as it rebounds. So we know that change in momentum is going to be the mass times change in the velocity. So the mass is 60 times 10 power negative 3, and the change in velocity. As it goes to the wall, the velocity is in the initial velocity in the horizontal, which is 7.5, minus as it rebounds, so it is minus negative. It rebounds with this velocity in the horizontal, so that is 4.6. So we add. So the change in momentum is going to be 7.5 plus 4.6 times the mass, 60 exponent negative 3. So that is 0.73. 0.726 or 0.73 Newton seconds. State and explain whether the collision is elastic or inelastic. You just even look at the velocities. It moves towards the wall with a velocity of 7.5. So the relative speed of approach is 7.5 minus 0, because the wall is not moving. It rebounds with a speed of 4.6. It means the relative speed of separation is still 4.6, because the wall will not move. Therefore, since the relative speed of approach is greater than the relative speed of separation, the collision is inelastic. So you can say relative speed of separation that is 4.6 minus 0 meters per second, is less is less than relative speed of approach. And this is 7.5 minus 0. 0 is for the wall, 7.5 is for the ball. So 7.5 minus 0 meters per second. The collision is inelastic. Hence, inelastic. Alternatively, you can check the kinetic energy. Of course, if the speeds are different, it means the kinetic energy is different. If the final speed is smaller, it means the final kinetic energy is less. Final kinetic energy is less. It is less than the initial. The final kinetic energy. The final kinetic energy is less than the initial kinetic energy. So it is what? Inelastic. Final kinetic energy is less than the initial kinetic energy. So the collision is inelastic. Okay. The variation with time t of the displacement s for a car is shown in the figure. So it is displacement against time, and that is how the graph looks like. Determine the magnitude of the velocity between 5 seconds and 35. So we look for 5 seconds. The scale is 20 divided by 10, that is 2. On the x-axis, each small square is 2, so this is 2, 4. 5 seconds is in the middle here. So that is the point. 5 seconds is there in the middle. That is 5 seconds. And 5 seconds, the displacement is, on the vertical, it is 100 divided by 5, which is 20. So this is 40. And then 35. Remember, each small square is 2. So 1, 2, 3, 4, 5, that is 30. 32, 34, 35 is in the middle here. So 35 is in the middle there. So let's see. I'll put there a line. And I think it goes up to that point. So 35 is in the middle here. And the corresponding value of displacement is that is, I think that is 580. 580. Okay, so the corresponding value here is 580. This one is 40. So determine the magnitude of the average velocity. Velocity is going to be the area, the actual velocity is going to be the gradient of that line. So velocity is equal to the gradient. So the average velocity equals to the gradient. Because it is a displacement time graph, the average velocity is equal to the this is a graph of what? Displacement against time. So the average velocity is the gradient. Is equal to the gradient, which is going to be 580 minus 40 divided by 35 minus 5. Five 80 minus 40 divided by 35 minus 35, that is 30. So we are seeing that the average velocity is 18. On the figure, sketch the variation of the time t of the velocity v of the car. Okay, So let's look at this point. In the first few seconds, about 2 seconds, or it's about initially the velocity is 0, but because initially you see the gradient, the line is going, it gets to x-axis, so it means the initial gradient is 0. So the graph starts with 0 velocity and remains 0 up to around, this time is which time is this? It remains 0 up to around 2 seconds. Around 2 seconds it remains 0. Then after 2 seconds it slightly increases for almost, no, between 2 and 4 seconds it increases. The gradient increases, then the gradient becomes constant after 2 seconds. Around after 2 seconds the gradient becomes constant. Then it becomes constant. Then after around 35, then the gradient starts decreasing. Here the gradient decreases after 35. Then the gradient becomes 0 at this value is what? The gradient becomes 0 at around 40, is it 45? Yes, it is in the middle of this box. The gradient becomes 0 at 45. That means the velocity there is 0. So look for 45. We can start with 45. 1, 2, 3. 45 is here. So at this point, the graph should cross this point. And then it now again starts increasing. So this part here, the gradient is increasing, but in the opposite direction. So between 45 to around, I think it's before 60, the straight line stops around here. The straight line starts from around here. No, the straight line starts from around here. So that is around, remember each small square on the x is 2. So this is 1, 2, 3. 60 minus 6, that is 40, 54. At 54 or 53, around there, 54 or 53, the line stops being straight. I mean, the line starts being straight, so that means it becomes constant up to 100. So the most important values of time are going to be 35, 1, 2, 3, 4, 5, that is 30, 32, 34, 35 here. Between 35 and 45, this is 35 and 45. Here we see that the gradient is going to be constant, but the velocity is decreasing. It goes up to it crosses the x-axis. Then at a point closer to 60, that is around 54, 1, 2, 3, around 54, the graph reaches a maximum, a constant value. So we shall sketch this. Initially, the velocity is 0 because the gradient here is 0. I hope the scale is 20 divided by 10, that is 5, I mean 2. So this is 2, between 0 and 2, the gradient is 0. Then after 2, the gradient slightly increases up to around 2.5. So I'll have to draw a graph which goes upwards because the velocity increases. So between 2 and 2.5, which is somewhere here, there's an increase in velocity. So I'll draw a line which goes upwards. Because the curve is smooth, the gradient is increasing by equal amounts. That is too big. So this should be in this box here. Okay, so that is between around 2 to 2.5. There is an increase in velocity, then it becomes constant. It becomes constant at 2.5. Is it 2.5 seconds? That is 5. 2, 4, 5. At 5, it becomes constant until 35. So I'll draw a horizontal line until we reach 35. Let me increase the weight. So I'll draw a horizontal line up to 35. So there the velocity remains constant because we have a straight line for the displacement time graph. Then after that, the velocity goes to 0 because it decreases because we see a smooth curve whose gradient is decreasing. Between 35 and around 45, the velocity decreases to 0. So the graph goes to 0. So this will be a straight line going to 0 from 35. So this is in the middle of the box. Then there is a change in direction. The velocity increases, but in the opposite direction, because you see after 45, the gradient is increasing, but in the opposite direction. So the graph continues downwards up to around 35, time of 54 when it becomes constant. 54 or 53 around there. So I'll look for 54, 53. However, you also notice that the gradient on the left-hand side is smaller than the gradient on the right-hand side. Let's check. If we consider 580 minus 0 divided by 100 or divided by 50, I hope it is 54, 45, this is 46, 48, 50, 52, 54. So divide by 54 minus 100, let's check that. 580 divided by 54 minus 100. So you see that this gradient is 12. The other one was 18. So this is a smaller gradient. So this gradient is smaller, around 12. So it will be it goes to a maximum constant value which is less than the previous one. So this graph should not go further deeper than the one on top. So I'll take it down slightly up to around 54. 54 is somewhere there. Then it becomes constant because it now becomes a straight line. So then it becomes a straight line. Yes, so that will be our graph. That will be our graph. So this part here is smaller than the other part because the gradient for the first part was correspond to 18 and this gradient corresponds to 12, approximately 12. So it should be smaller than the other one on top. Okay. So that is the simple question of kinematics. Sorry about that. The variation with time t of the velocity v of a car is shown in the figure. So that is our figure. We can have a look at it. Okay. So at time t equals 0, the driver sees an obstacle in the road. A short time later, the driver applies the brakes. The car travels in two stages as shown. Use the figure to describe the velocity of the car in stage 1. So stage 1, you see that the velocity is constant. So that is constant speed or constant velocity. Stage 1, that is constant velocity. Stage 2, the velocity is decreasing, but is decreasing uniformly. So it is a constant rate of decrease in velocity or uniform decrease in velocity, which you can call a uniform deceleration. So it is a constant rate of decrease in velocity. Constant rate of decrease in velocity. Then calculate the distance traveled by the car from t equals to 0 to t equals 3.5. That means it is the area under the graph. So distance is equal to the area under the graph. Area under the graph, and that will be for both stages. Therefore, let's start with stage 1. Stage 1, distance equals to stage 1, we can consider it as a rectangle. Stage 1 we can consider it as a rectangle. So this is the x-axis is 0.05. This is 55665. I think that is 0.65. So we are going to say 0.65 times on the vertical. On the vertical, I think this is 5 divided by 5, that is 1. So this is 18. On the vertical, it is 18. So it is 0.65 times 18, which gives us that distance. So that is 11.7 meters. Then stage 2 is a triangle. The distance is going to be equal to a half times the base. From 35 to 0.65, I mean 3.5 minus 0.65, that is the base. Then times the height. The height is the same. It is, I think it is 9. I mean it is 18. So the height is the same, it is 18. So that gives us a half, 0.5 times 18 times 35, I mean 3.5 minus 0.65. So that is 25.65 or 25.7. Okay, so total distance is the sum. Total distance will be equal to 11.7 plus 25.7, which gives us 37.4. You would also have considered this shape as a trapezium. It can also be considered as a trapezium. where A will be 0.65 and B can be 3.5 and the height will be 18. You'll get the same answer. Okay, then the car has a total mass of 1250 kilograms. Determine the total resistive force acting on the car in stage 2. Total resistive force acting on the car in stage 2. So we can use, I'll do many methods here. Method number 1, I can use force equals to mass times acceleration. So the acceleration is going to be the force. The acceleration is going to be the force over the mass, but then we know that acceleration is equal to in stage 2, the velocity changes from 18 to 0 in a time of 3.5 minus it starts changing at 0.65. That is the acceleration. So the acceleration is going to be change in velocity over time, which is 18 divided by 3.5 minus 0.65, which is 6.3. So the acceleration is 6.3. Now I can find the force F. So F is equal to the mass, which is 1250 times 6.3. So 1250 times 6.3, that is 7875. 7875 newtons. That is method 1, which means the force is approximately 7900 newtons to two significant figures. So consider this as method 1. Method 2, you can use the definition of force as the rate of change of momentum. So force is equal to the rate of change of momentum. The change in momentum, because mass is 1250, that is m times v. The change in velocity is from 18 to 0. So that is from 18 to 0. The time it takes is still 3.5 minus 0.65. So this is going to be 1250 times 18 divided by the change in time is 3.5 minus, so this is 3.5 minus, not 3.5 minus 0.65, which gives us the same things, approximately the same 7894. 7894, which rounds off to 7900. That's method 2. Method 3, you can use energy conservation, kinetic energy. We know that kinetic energy EK is a half mv squared, which will be equal to a half times the mass 1250 times v, which is 18 squared. So the change in kinetic energy is from when the speed is 18 up to when the speed is 0. And the work done is equal to change in kinetic energy, which work done is force times distance. We have seen the distance when the speed changes from 18 to 0, which distance was 25.7 meters. Therefore, the force is going to be the work done, which is a half times 1250 times 18 squared, that's the work done, divided by distance, which is 25.7. Let's check. A half, 0.5 times 1250, then times 18 squared, divided by 25.7. That is 7879. 7879. So all these values are rounding off to 7900 to two significant figures. So you can choose any method to determine the total resistive force. For safety, drivers are asked to travel at lower speeds. For each stage, describe and explain the effect on the distance traveled for the same car and driver traveling at half the initial speed. For the first stage, if the car is moving at half the initial speed, it means the distance covered is going to be half in the same time for stage 1, because the time is not changing. So the distance is going to be halved because the distance is area under the graph. So if we say half If we say half of 18, that would be 9. Half of the speed, and you see that the area here is half, which means the distance is half. The distance is half since the speed is half. So distance is half since the speed is half. Since the speed is half, but the time is the same. So if the time is the same and yet the speed is half, it means the distance will also be half. So half the speed. Then here, since it is half the speed, so I will draw another line here which goes to 0. There's also the distance reduced by half. Okay, so in stage 2, yes, the acceleration is going to be the same. The acceleration is going to remain the same. And if we consider the equations of motion, then you realize that actually here for stage 2, for the same time, if the speed is half, let's use the equations of motion. If we say v squared equals to u squared plus 2as, final velocity is 0. 0 is going to be equal to initial velocity, which is u squared, minus 2as, because it is a deceleration. So that means the distance covered s is equal to u squared divided by 2a. Now, if u is halved, if the speed is halved, if the speed is halved, so it means the new value of s is going to be equal to a half of the initial value, but this is squared, then divided by 2a. That means this becomes a quarter into u squared divided by 2a, which means that the new displacement is a quarter of the original displacement. That's what it means. Therefore, here we are simply going to say that if the acceleration is going to be the same, the acceleration is the same. The acceleration is the same, and from s equals to u squared over 2a, and the new value of speed, the new value of speed is going to be equal to a half of the initial value, which implies that the new value of displacement is going to be a half u squared divided by 2a, which is actually a quarter into u squared over 2a, which is a quarter of the original value of displacement. So the distance is going to be a quarter of the distance before. So the distance covered, if the velocity is halved, the distance covered is going to be a quarter of the initial distance or the distance before. That is, if the velocity is halved, because they wanted us to describe and explain the effect on the distance traveled for the same car, the driver traveling at half the initial speed. So it means the deceleration to 0 is going to remain the same when you travel at half the initial speed. So the acceleration is the same. That's why I maintained a. But the initial speed is not going to be the same. Therefore, if the initial speed is halved, it means the distance covered is going to be a quarter of the distance before. Okay, define acceleration. We know that acceleration is the rate of change of velocity. rate of change of velocity, or change in velocity over time taken. Change in velocity divided by time taken. State Newton's first law of motion. A body continues at constant velocity unless acted on by a resultant force. A body stays at rest or continues with a constant velocity unless acted on by a resultant force. A body stays at rest or continues moving at constant velocity unless acted on by a resultant force. So if there is no resultant force acting on a body, it will either stay at rest or it will continue moving with a uniform velocity. That is Newton's first law. It will continue moving with a uniform velocity. That is according to Newton's first law. The variation of t of the vertical with the t of the vertical speed v of a parachutist falling from an aircraft is shown here. So initial velocity is 0. Initially the velocity is constant, then it starts initially the velocity is increasing uniformly, so the acceleration is constant. Then it starts decreasing, and at b it is completely constant. Then after it starts decreasing uniformly, then at a point close to D, it starts decreasing non-uniformly, and then at E it becomes constant. Okay, calculate the distance traveled by the parachutist in the first 3 seconds. So distance is going to be the area under that graph. So distance equals to the area under the graph. And when you look at the graph, you see the first 3 seconds. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So you have 10 divided by 25. 10 divided by 25. I'm establishing the scale on the x-axis. It is 0.4. So we want the first 3 seconds. 3 divided by 0.4. Those are 7.5 small squares. 1, 2, 3, 4, 5, 6, 7.5. So 7.5 small squares. I will draw a vertical line here. I think it goes to that point. So 7.5, it takes us to this value here, which I think on the vertical it is 29.5, because on the vertical axis the scale is 1, 1, 2, 3, 4, 5, 6, 7.5. It is slightly here. It is actually in the middle of the box. It is not exactly there. It is in the middle of the box. So it is inside here. That is 29.5 in the middle of the box. So it is somewhere here, which is in the middle of this box. and the middle of the other box for 7.5. Okay, so we are finding the area under the graph, which is a half times the base, which is 29.5 times, no, this is not 7.5, it is just 7.5 small squares, giving us 3. This is 3. 3.0. So we now just multiply this by 3, and this gives us 0.5 times 2.95, then times 3, which gives us 4. Sorry, it is 0.5 times 29. This is 29. 0.5 times 29.5, then times 3, which is 44.25. 44.25, which is approximately 44.3. Explain the variation of the resultant force acting on the parachutist from t equals to 0 to t equals to 15 seconds at point C. Okay, so we are talking about resultant force. So for the first 3 seconds, here acceleration is constant because it's a straight line. So the resultant force here is constant. After 3 seconds, then the resultant force must be decreasing because the gradient is decreasing, the acceleration is decreasing up to around point B. Then after point B, the resultant force must be 0 because the acceleration is 0, the gradient is 0. That is how the force is varying here. So what happens after point B? It means that at that point between B and C, the force due to friction or resistance or air resistance must be equal to the weight at that point. Therefore, we shall say that the resultant force, because the parachutist is falling downwards, the weight is downwards, air resistance is upwards. So all the friction force is upwards. So we shall say resultant force is equal to the weight minus the frictional force. So at the start, the frictional force is equal to 0. That's why the resultant force was constant. At the start where V is 0, at the start, friction force or frictional force, at the start frictional force is equal to 0. Then frictional force starts increasing. Then frictional force increases, of course, with the speed. Then frictional force increases with speed. Then frictional force increases with the speed. And we see that at the end, that is between B to C, at the end, that is B to C. At the end, B to C, the frictional force equals the weight. So initially the resultant force, remember, resultant force is equal to the weight minus the frictional force. But at the start, frictional force is 0. That means the resultant force is going to be just constant because the acceleration is going to be constant. Then after, frictional force increases with the speed, and and at the end, not and the end, and at the end, the frictional force equals to the weight. Thus, the resultant force becomes zero, where the resultant force becomes zero. At that point, when the frictional force starts increasing, the resultant force actually decreases. And then at the end, that is B to C, where the frictional force equals to the weight, the resultant force becomes zero. As simple as that. Okay. Describe the changes to the frictional force on the parachutist at t equals 15 seconds. At t equals 15 seconds, so at t equals 15 seconds, we see what happens at t equals 15 seconds. You see that now after 15 seconds, the velocity decreases. That means the frictional force must have increased. So the frictional force increases. So frictional force increase. Frictional force increases. Then between t equals to 0, t equals to 15 seconds and t equals to 22 seconds. That is at point E. Between point C and point T, describe the changes. Describe the changes to the frictional force on the parachutist. So here again, you see that it is a straight line between C up to around closer to D. It is a straight line. That means frictional force, of course, it has increased, but is constant. That's why there's a decrease in speed. Frictional force increases. It has increased at C, but now it is constant because it's a straight line. And then after, when you turn towards E, it again decreases because the gradient decreases. That means the resultant force is actually the decrease in speed is reducing. That means the frictional force is actually decreasing. Then we can simply say that between C and D, the frictional force is initially constant. Frictional force is constant. And then it decreases. And then it decreases. The mass of the parachutist is 95 kilograms. Calculate for the parachutist between t equals 15 to t equals 17, average acceleration. Of course, we know that acceleration is equal to change in velocity over change in time, which will be maybe v2 minus v1 over change in the value of time. So let's see the change in the values of v between t equals 15 and t equals to 17. T equals to 15 and t equals to 17. 15 must be the center. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 14, 13, 12, and 5. I think 15 is there. So 15 is in the middle of this box, and then 17. So 15 is there. Then 17. Remember, each small box is 0.4. So 15.4. How many boxes for 17? 17 minus 15 times 0.4. So I'll add 5 small squares. That's 1, 2, 3, 4, 5. I think 17 is somewhere there. Seventeen must be somewhere here. So 17 is at 20 and 15 is at 50. So from the graph, 17 is at 20 meters per second and 15 is 50 meters per second. So we just subtract. The acceleration will be 20, final is 20, initial is 50. The time is from 15 to 17, which gives us 20 minus 50 divided by 2, which is negative 15. So the acceleration is negative 15. Of course, the negative is just showing a deceleration. The average frictional force. We want to calculate for the parachutist in that time the average frictional force. Since we have the deceleration, of course, we know if the parachutist is falling downwards and the frictional force is upwards, so the weight minus the frictional force is equal to the mass times acceleration, which is the resultant force. The weight minus the frictional force must be equal to the resultant force. But remember, the acceleration is negative. So if I use this expression, I must indicate a negative there. If I don't want to use that negative, I can do it the other way around. And I say the frictional force minus the weight is equal to ma, because the frictional force is greater than the weight. So here I will not use the negative on acceleration. So the weight is going to be mg. So that is mg minus the frictional force, which I want, is equal to m times a. So m is 95 times g, which is 9.81, minus the frictional force equals to m, which is 95, times the acceleration, which is negative 15. So if I take F frictional force on one side, so frictional force will be equal to 95 times 9.81 plus 95 times 15. So you can also check your calculator. 95 times 9.81 plus 95 times 15. So this gives us 2356, or 23, that is 2356.95. Alternatively, you can use this. So the frictional force is equal to ma plus the weight. That means this time you not use the negative. So you just say ma, which is 95 times 15, plus the weight, which is 95 times 9.81. So that would give you the same value. So this is approximately 23 or 2400. So that is 2400 newtons. The drag force D of an object on an object of cross-sectional area A moving with a speed v through a fluid of density rho is given by that expression. Show that C has no units. So I make C the subject straight away. C is going to be twice d divided by density area v squared. That is making d the subject. C the subject. D is force. So the units of D are going to be kilogram, meters per second squared. Then A is area, that is meters squared. V is speed but is squared, so I will write meters squared per second squared because V is squared. Then rho is density, so that will be kilogram per meters cubed. I think that is all. We just substitute now the units. The units of C will be for D, which is kilogram, meters per second squared divided by density, which is kilogram per meters cubed times meters squared per second squared. So we now simplify this. In the numerator we remain with, we have kilogram meters per second squared divided by, in the denominator we have kilograms, meters power negative 3 times meters squared, you remain with the meters power 1, then times s power negative 2. So you realize that each of these quantities in the bottom has its corresponding quantity in the top, so they cancel out. So just conclude that C has no units. You just conclude that C has no units. A rainy drop falls vertically from rest. Assume that air resistance is negligible. On the figure, sketch a graph to show the variation with the time t of the velocity v of the raindrop for the first 1.0 seconds. Air resistance is negligible. That is a straight line since the acceleration is constant. And it will be falling due to gravity. For the first 1.0 seconds, v equals to u plus at. V is going to be equal to, since it falls, initial velocity is 0. So this will be 9.81 times t, which is 1 second. So the graph must be at around 9.8. So 9.8 at 1. When t is 1, it is at 9.8, around here. The scale on the vertical is 2 divided by 5, which is 0.4. 8.4.8, 9.2, 9.6, 9.8. So it is around there. So I'll draw a straight line. It is here. Okay, so that is for the first 1 second. I think the line goes up that point. Then calculate the velocity of the raindrop after falling 100 meters. After falling 100 meters, of course, we can use equations of motion such as v squared equals to u squared plus 2as. V squared is u squared plus 2as. It is falling from rest, initial velocity is 0. So we shall say that v squared is equal to 0 squared plus 2 times 9.81, then times s, it will fall through 1,000 meters. So we have 2 times 9.81 times 1,000, which is going to give us that. Then we find the square root. The square root is 140. So this means that v is equal to 140. So the answer here is 140. We can use conservation of energy, and where we can say, alternatively, we can say the loss in gravitational potential energy is equal to the gain in kinetic energy. So the loss in gravitational potential energy is mgh. The gain in kinetic energy is a half mv squared. So m has cancelled. We want v. So v will be equal to the square root of 2 times g, which is 9.81, times h, which is 1000. So 2 times 9.81 times 1000 under the square root. So that is 140. So the answer there will be 140. In practice, air resistance on the oil drops is not negligible because there is a drag force. This drag force is given by the expression in A. State an equation relating the forces acting on the raindrop when it is falling at terminal velocity. So if it is falling downwards, the weight is W, there is upthrust upwards. Of course, there is drag force, which or air resistance on drop is not negligible because there is a drag force. The drag force is given by that expression. So state an equation relating the forces acting on the raindrop when it is falling at terminal velocity. At terminal velocity, the resultant force is 0, which means the weight downwards is equal to the upthrust plus the drag force. So that is the expression. The raindrop has a mass of 1.4 times 10 power negative 5 kilograms and the cross-sectional area 7.1 times 10 power negative 6 meters squared. The density of air is 1.2 kilograms per meters cubed, and the initial velocity of the raindrop is 0. The value of c is 0.6, show that the terminal velocity of the raindrop is 7 meters per second. Show that the terminal velocity is 7 meters per second. Okay. So when you look at the cross-sectional area of the raindrop, it is too small. That means the upthrust is going to be extremely small and negligible. So to begin with, I would say the upthrust is very small. The upthrust is negligible because the cross-sectional area is very small. So the upthrust is too small and negligible. So it is approximately 0. So it means the weight, which is equal to mg, should be equal to the drag. The weight is going to be equal to the drag if the air resistance is negligible. I mean the upthrust is negligible. So we shall have the weight is 1.4 times 10 power negative 5 times g, which is 9.81, should be equal to the drag force. The drag is given by this expression. Where is the expression? The drag is given by this expression here. These are half times c rho a v squared. So I'm just substituting. So d will be equal to the drag will be a half times c, which is 0.60, times density, which is 1.2, times the cross-sectional area, which is 7.1 times 10 power negative 6, and then times v squared. So I'll check with my calculator. 1.4 exponent negative 5 times 9.81, then times 2, then I divide both sides. So I'll divide by 0.6 times 1.2 times 7.1 exponent negative 6. Then I find the square root, which is 7.33, approximately 7. So V is 7.33 or approximately 7 meters per second as required. Am I writing meters per second? It is unique. For the raindrop, the raindrop reaches terminal velocity after falling approximately 10 meters. After falling approximately 10 meters. On the figure, sketch the variation with the time t of the velocity v for the raindrop. The sketch should include the first 5 seconds of motion. So it reaches terminal velocity after falling a distance of 10 meters. So let's find the approximate time for which it reaches terminal velocity. Approximate value of time for which it reaches terminal velocity. So if we assume that v, if we assume that v is equal to u plus at, although this is not constant, let's say v is what we want to find. We want to find the approximate velocity for which it reaches terminal velocity. And the terminal velocity is, approximately 7, or let me say 7.33 is equal to initial velocity is 0, acceleration, let's say it is approximately, which acceleration should I use? Okay, let's check for the distance, is 10 meters. Let me use an equation which has distance, because they said it reaches a terminal velocity after traveling a distance of approximately 10 meters. If the terminal velocity is approximately 7.33, let's check. So I'll use an equation which has distance. Let me use S equals to, should I use S? Equals to ut plus a half at squared. Of course, at terminal velocity, acceleration will be 0. At terminal velocity, acceleration is 0. So S will be equal to 10 is equal to initial velocity. No, that one will also not work because it fell from rest. S is 10, then T, I think that will also not work. Let me use S equals to, assuming the distance is area under the graph, then we estimate that is going to be a triangle. So the distance is going to be a half of time times the terminal velocity, 7.33 on the vertical. I'm estimating it to be approximately initially triangle before terminal velocity, because we know the graph is going to look like this. Then it becomes horizontal. So I'm estimating this part here to be approximately a triangle. So this means the distance is 10 equals to a half times t times 7.33, or 7. Terminal velocity is approximately 7. Let me use 7. This is an estimate. So it means the time t is going to be 20 divided by 7. 20 divided by 7, that is around 2.85. So at around 2.85, then the body must have reached terminal velocity. So when I'm sketching my graph, I'll concentrate on that. Let me leave this because this will not work. Estimate the time. What is important is the estimate time for which it reaches terminal velocity. So I've assumed when it reaches terminal velocity, the speed remains constant. So the area under that part is approximately area of a triangle. Approximately. So that's why I've said distance is a half t, that is the base. If this is t, then times the velocity, it will have reached, that is 7. So my graph must be horizontal by the time we reach 2.85. So I'm now going to sketch a graph. At around 2.85, I think 2.8 is around here. The graph must have become horizontal, and it must be at terminal velocity, which is 7, 1, 2, 3. So 7 is in this line here. So I know that after 2.85, that will be a horizontal line. So I'll draw a horizontal line already. So there is a horizontal line. That means the other part, the graph is not going to be a horizontal line, it is going to be a curve. It is going to be a curve. So this is going to be a curve which becomes horizontal at this point. So the graph would look like that. Two planks of wood, AB and BC, are inclined at an angle 15 degrees to the horizontal. The two wooden planks are joined at point B as shown in the figure. Okay, so a smaller block of metal M is released from rest at point A. It slides down the slope to B and up the opposite side to C. Points A and C are 0.26 meters above B. Assume frictional forces are negligible, so equations of motion can apply here. Describe and explain the acceleration of M as it travels from A to B and from B to C. So the acceleration is going to be, since air resistance is negligible, the acceleration from A to B is the same as from B to C. Only that they will be in opposite directions. From A to B, the acceleration is towards B, downwards. From B to C, the acceleration is still towards B, downwards. So they are equal in magnitude, but in opposite directions. So we can say accelerations from A to B and B to C and, and B to C have the same magnitude but are in opposite directions. So we can say from A to B. What contributes to this acceleration? From A to B and B to C. It's actually the component of the weight down the slope which provides the acceleration. It's the component. It's the component of the weight down the slope. It is the component of the weight down the slope which provides the acceleration. It's the component of the weight down the slope which provides the acceleration. If we consider the mass at M, its weight vertically downwards, mg can be resolved into mg sine of 15 down the slope. Even when it is here, it will be mg sine 15 down the slope. So if you remove m, it means the acceleration down the slope is g sine 15. Even at c, it will be g sine 15. So we are saying from A to B and B to C, it's the component of the weight down the slope which provides the acceleration. And accelerations from A to B and B to C and B to C have the same magnitude have the same magnitude but are in opposite directions. but they are in opposite directions. In fact, they are both towards B. Both directed towards B. So calculate the time taken for M to travel from A to B. One time taken to travel from A to B. Since air resistance is negligible, we can simply use equations of motion, but we need to note that, or we need to find the correct acceleration. We need to find the correct acceleration. Or alternatively, we can use, we can say if the body is moving downwards and air resistance is negligible, it means the resultant force is just down the plane. There is no friction. So the resultant force down the plane is mass times acceleration, which is given by mg sine of 15 down the plane. So if we want the time, we can now use that acceleration to find the time. Okay. So MA resultant force is MA, which is equal to mg sine of 15 down the plane. So it means the acceleration is simply going to be equal to g, which is 9.81 sine of 15. That is the acceleration. So if you want now to find the time from A to B, we can now use equations of motion. S is equal to ut plus a half at squared. S can be found. That is the distance down the plane. Let's find S from here. S is the distance AB. We have opposite hypotenuse, that is sine. So we have that sine of 15 is equal to the opposite, which is 0.26 divided by the distance AB. So sine of 15 is equal to the opposite, which is 0.26 divided by the distance AB, which implies that the distance AB is equal to 0.26 divided by sine of 15. Remember, it starts from rest, so initial velocity is 0. Now we are substituting. So the distance AB is 0.26 divided by sine of 15. Initial velocity is 0 plus a half times acceleration, which is 9.81 sine of 15, then times the time squared. So we have 0.26 divided by sine of 15, then times 2 divided by open brackets 9.181 sine of 15. Then we find the square root. We are getting 0.88955, so that is 0.89. So the time is 0.89. Calculate the speed of m at B. Still, we can use equations of motion, or we can use conservation of energy. Let me start with the equation of motion. So method 1, I will use equations of motion. V equals to U plus AT. We now know the acceleration is g sine 15. So V is going to be initial velocity 0 plus 9.81 sine of 15. Then we multiply this by the time. Of course, the time we have got it as 0.89. So V is going to be 9.81 sine of 15, then times the time, which is 0.89. So that is 2.26 meters per second. That's method 1. Method number 2, we can use kinetic energy. We can use kinetic energy where we can say the loss in potential energy should be equal to the gain in kinetic energy. So the loss in gravitational potential energy should be equal to the gain in kinetic energy. So the loss in potential energy is mg times h. The gain in kinetic energy is going to be a half mv squared, and we want v. So m cancels. In this case, we don't use the component of g down the plane because we are not using the acceleration. We are looking at the vertical. So it means h is going to be, h I think was 0.26. So I'll simply say 0.26. H, this is 9.81 times 0.26 is equal to a half times v squared. So I'll just press the calculator to get v. 9.81 times 0.26 times 2, then square root. So we are getting 2.26 meters per second. So that's the second method. I think those methods are enough. So you can use energy, you can use equations of motion. So this was method number 2. The plank BC is adjusted so that the angle it makes with the horizontal is 30 degrees. M is released from rest at point A and slides down the slope to B. It then slides a distance along the plank from B towards C. Use the law of conservation of energy to calculate this distance. Explain your working. We are going to use the law of conservation of energy to calculate the distance. The plank BC is adjusted so that the angle it makes with the horizontal is 30 degrees. M is released from rest at point A. So they have increased the angle for BC. So BC has been increased to 30 degrees. BC has been increased to 30 degrees. Okay. So it means the height h must have changed. The height h must have changed if we consider the same position of the 0.26. So let's say the loss in gravitational potential energy at A must be equal to the gain in gravitational potential energy at B. At C. So the loss in gravitational potential energy at A was mg. Let's say the height is h1 because AB was not changed, but BC was changed. So the gain here is going to be mg times h2. Of course, mg cancels, g cancels. So do we notice that h1 is going to remain the same as h2? But remember, h1 did not change. h1 was 0.26. So this is going to be 0.26 meters. That is the vertical height. The vertical height has not changed. It is still 0.26 meters. The vertical height where the object moves does not change. It is on side BC. So this is what is happening. We have the horizontal and the angle has become 30 degrees. So we are saying the vertical height h is still 0.26 meters. All we need is this distance here, distance x. So as a mathematician, you will notice that if I want x in the hypotenuse, that is sine. So sine of 30 is equal to the opposite, which is 0.26 divided by hypotenuse, which is x. So it means x is equal to 0.26 divided by sine of 30, which is 0.26 divided by sine 30, that is 0.52. So x is 0.52. X is 0.52. Define power. Of course, we now know that power is the rate of doing work. It is actually work done over time taken. So that is, you can define power as work done over time taken. A cyclist travels along a horizontal road. The variation with the time t of the speed is shown in the figure there. So we have drawn the graph for speed against time, and we see that the gradient decreases. Describe and explain the motion of the cyclist. The cyclist maintains a constant power and after some time reaches a constant speed of 12 meters per second. Okay, reaches a constant speed of 12 meters per second. That is later on. It is not shown on the graph. Describe and explain the motion of the cyclist. Using that graph, I said in kinematics we describe motion. So we see that as the speed increases, of course, air resistance must be increasing because we see that the gradient is decreasing. Air resistance decreases or the drag increases, which means the resultant force reduces, so the acceleration reduces. The speed will then become constant later on, that is at 12 meters per second, when the resultant force is zero and the acceleration will be zero at that point. So therefore, we can simply say as speed increases, air resistance which I'm calling the drag, increases. The resultant force reduces. Remember the cyclist is traveling, air resistance is in the opposite direction. So as the speed increases forward, air resistance also increases in the opposite direction. So the resultant force decreases. Hence, acceleration also reduces. That's why we are seeing on the graph that the gradient is decreasing because the acceleration is reducing. The speed will then become constant. The speed will then become constant when the resultant force is zero. The speed will then become constant when the resultant force is zero, and of course the acceleration will be zero. And the acceleration will be zero or will become zero. So when the speed becomes constant is only because the resultant force is zero. That means the air resistance is balancing with the driving force of the cyclist. Okay. When the cyclist is moving at a constant speed of 12 meters per second, the resistive force is 48 newtons. Show that the power of the cyclist is 600 watts. Explain your working. So When the speed is constant, it means the force from the cyclist must be equal to the resistive force. So at constant speed, this part of explaining your working is very important. At constant speed, the force from the cyclist should be equal to the resistive force. So the force from the cyclist should be equal to the resistive force. So we want the power of the cyclist to show that the power of the cyclist is about 600. So power is equal to the force times the velocity. Since the force from the cyclist is equal to the resistive force, this will be equal to 48 times 12, which is going to be 48 times 12, which is 576, which is approximately 600 watts. Use the figure to show that the acceleration of the cyclist when his speed is 80 meters per second is about 0.5 meters per second squared. So, of course, for acceleration, we find the tangent, the gradient, because a velocity time graph, its gradient is the acceleration. Now we have to look for the acceleration at 0.5 meters per second, which would be equivalent to drawing a tangent at 8.0, at a time of, at a speed of 8.0 seconds. So consider a tangent. I'm just writing this here for explanation. Consider a tangent at 8.0 meters per second on the graph. So let's go to the graph and draw the tangent of 8.0 at 8.0 meters per second. So 8.0 meters per second is here. So this is the point. So I have to draw a tangent. I have to draw a very neat tangent there. Okay, so I'm trying to draw a tangent, which is not easy. Okay, so I've tried to draw a tangent there, so I'm going to find the gradient. I'm going to find the gradient of that tangent. So here, I'm going to assume it is at, the scale here is 0.2, so this is 4.8. On the vertical here, I can take it up to, I will take it up to the end. So I'll take it up that point. Okay, so I'll take it up that point to find the tangent. So this is the point I'm going to consider. On the vertical, it is 12 minus 4.8. Then on the x-axis, I think this is downwards. I'll put the ruler to see. So that is 15 point what? On the x-axis, the scale is 2/5, which is 0.4. So this is 14.4, 14.8, 15. That is 15.2. Okay, so I'm finding the gradient. To find the acceleration, I'm finding the gradient because the gradient is the acceleration from a velocity time graph. Okay, so the acceleration is equal to the gradient, which will be equal to, on the vertical we have 12.0 minus 4.8, divided by, on the x-axis we have 15.2 minus 0. We may not use the same points, but you can have your own values. 12 minus 4.8 divided by 15.2. So that is 0.47. So this is 0.4774, or approximately 0.5 meters per second squared as required. You can get a different value, but rounding off to 0.5 for that gradient. The total mass of the cyclist and the bicycle is 80 kilograms. Total mass is 80 kilograms. Calculate the resistive force R acting on the cyclist when his speed is 80 meters per second. Use the value for the acceleration given in part 3. So they have given us the total mass of the cyclist. We know that the resultant force, which is given by mass times acceleration, is going to be actually the difference between the force from the cyclist minus the resistive force R. So the resultant force is going to be 80 times the acceleration, which is 0.5, which is going to be equal to the force from the cyclist. We have already seen the force from the cyclist will remain the same, which is 570. The force from the cyclist is the power divided by the velocity, which this time it will be 576 divided by the velocity, which is 8. That's the force from the cyclist. The power will remain the same because they said the total mass of the cyclist is that. Calculate the resistive force. When the cyclist is moving at constant speed, the resistive force is that. Show that the power of the cyclist is 600 watts. So I'm using 576 instead of 600 to be more accurate. So this is going to be 576 divided by 8, then minus the resistive force. Minus the resistive force R. So it means R is going to be equal to 576 divided by 8 minus 80 times 0.5, which is 32. So the resistive force is equal to 70 minus 72 minus 40, which is equal to 32. So that is 32. Use the information given in Roman 1 and your answer in part 4. Roman 2 and part 4 to show that if the situation, in this situation, the resistive force R is proportional to the speed V of the cyclist. Let's check. If they are proportional, it means when I divide R over V, I should get a constant. So at 12 meters per second, R divided by V is equal to, R was at 12, what is R? At 12 meters per second, R was, is it 40? R was 48. At 12 meters per second, R was 48. So R over V is equal to 48 divided by 12, which is 4. Then at 80 meters per second. At 80 meters per second, the drag force R is 32 newtons. Then here R over V is equal to 32 divided by 8, which is equal to 4. So since R over V is a constant, then R is directly proportional to V. Since R over V equals to a constant, then R is directly proportional to V. As simple as that. Define velocity. So we now know that velocity is the rate of change of displacement. That is velocity. Acceleration, that is the rate of change of velocity. Okay, rate of change of velocity. A car of mass 1,500 kilograms travels along a straight horizontal road. The variation with the time t of the displacement x of the car is shown here. So this graph is for displacement against time. Okay, we can first see the most important points where it stops here. It stops around the scale on the vertical is 20 divided by 10, which is 2. That's 122. 122 there. Then use the information, use the figure to describe qualitatively, no need of quoting values, the velocity of the car during the first 6 seconds of the motion shown. Give reasons for your answers. So initially we see a straight line, then the gradient reduces, and finally we see a straight line. Somewhere here, the gradient is reducing and then it is constant. So we have initial constant velocity, then we have a decreasing velocity, and then finally we have again a constant velocity but lower than the one which was at the start because it is of a smaller gradient. Okay, so you can say initially velocity is constant because they said give reasons for your answers. Initially velocity is constant as it is a straight line. It is a straight line means constant gradient. Then the velocity decreases. Then velocity decreases. Then velocity decreases after about 2 seconds. As the gradient of the line decreases, we see that after about 2 seconds, the gradient decreases. As the gradient of the line decreases. The gradient of the line decreases. I think this goes on up to about 4 seconds. Up to about 4 seconds. Finally, in the last section, the velocity is constant. Velocity is constant. but it is going to have a lower value, but lower than at the start. But lower than at the start. Evidence: the gradient is constant and smaller than at the start. It is constant because it is a straight line, but it is smaller. It is smaller than at the start. Okay. So we can see initially it is a straight line, meaning constant gradient, velocity is constant. After about 2 seconds, the gradient decreases, it means the velocity decreases. And last section, after about 4 seconds, we see that the line again becomes constant, but when you compare the gradient in this section and the last section, you see that the gradient in the last section is smaller. So it means the velocity is constant, but at a lower value than the first stage or first section. Okay. Calculate the average velocity during the time t equals to 0 to time t equals to 1.5. So 1.5, 1, 2, 3, 4, 5. I think this is 1.5. So we want to find the average velocity, so that is going to be simply the gradient. So this is 1.5, and here it is 1, 2, 3, so that is 46. So velocity is equal to the gradient, and this will be equal to 40, is it 45, 46? 1, 2, 3, 4, 5. It is in the center, it is not 46. It is somewhere here in the middle of the box. If you printed this in large format, it is 45. So that is going to be 45 minus 0 divided by 1.5 minus 0. So 45 divided by 1.5, that is 30. Average velocity is going to be 30 meters per second. Show that the average acceleration between t equals to 1.5 and t equals to 4.0 seconds is negative 7.2. So between t equals to 1.5, we have seen the velocity at 1.5 meters per second, 1.5 seconds is 30 meters per second. All we need is to find the velocity at 4.0 seconds. From the graph, velocity at 4.0 seconds, we you can even use this because after 4.0 seconds, at 4.0, it is already a straight line. So we can find the velocity of the straight line considering from, I think at 4.0, that is around 90, is it 98? Let me use a ruler at 4.0. Okay, so 4.0, so that is 98. So you have 122 minus 98, then 6.0 minus 4.0 to find the velocity. So velocity at 4.0 seconds is equal to 122 minus 98 divided by 6.0 minus 4.0. I'm just finding the gradient of a line because it is a straight line. The velocity is constant at 4 as it is at 6. So this is going to be equal to 122 minus 98 divided by 2, that is 12. So that is the velocity. So now we can find the acceleration. Acceleration is going to be change in velocity divided by change in time. So the change in velocity is going to be 30, or 12 is the final, minus 30 divided by time between 4 and 1.5. That is 4.0 minus 1.5. 12 minus 30 divided by 4 minus 1.5, which gives us negative 7.2. Calculate the average force acting on the car between t equals to 1.5 and t equals to 4.0. We have got the velocity, the acceleration is negative 7.2. So force is equal to mass times the acceleration. So this mass the mass was, I think, 1,500. The mass was 1,500. And the acceleration is negative 7.2. So this gives us 1,500 times the answer, which is negative 10,800, or approximately negative 11 or 11,000. You may put the negative if you want. A trolley moves down a slope as shown in the figure. We can first of all see the forces acting. The weight is vertically downwards. There's a component of the weight down the plane, which we have now seen as weight W sine of 25. That is down the plane. The slope makes an angle 25 degrees with the horizontal. A constant resistive force Fr acts up the slope on the trolley. At time t equals 0, the trolley has velocity 0.5 meters per second down the slope. At time t equals to 4, v is 12 meters per second down the slope. So that the acceleration of the trolley is that. So for acceleration is change in velocity, v minus u over t. So just substitute, v is 12 minus 0.50. The time is from 4 to 0, so that is over 4. So that is simply going to be 12 minus 0.5. 12 minus 0.5 divide by 4. So that is 2.875, which is approximately 3 meters per second squared as required. Then calculate the distance x moved by the trolley down the slope between that time. Okay, so distance x, I may use one of the equations, such as s is equal to a half into u plus v times t, average velocity times time, because the velocity is increasing. There's a constant resistive force Fr. So this is going to be a half into 12 plus 0.5, then times the time is from 0 to 4, so the time is 4. So that is 12 plus 0.5 divided by 2 times 4, which is 25. So x is 25 meters. On the figure, sketch the variation with time t of distance x moved by the trolley. The speed is increasing. That means the gradient of the graph must be increasing. And if I am to stop at 4.0, my graph should be steeper at 4.0. but initially its speed is at t equals to 0, the trolley has velocity of 0.5. That means initially the gradient at t equals to 0, the gradient should not be 0. Remember, this is a graph of displacement against time. So at t equals to 0, the gradient should not be 0. So I can't draw a graph which is very horizontal at 0. So it should have some gradient at t equals to 0 so that there is a displacement. When there is a gradient, it means the velocity is not initially 0. Although the displacement is initially 0, the velocity is not initially 0. But the velocity is increasing from 5 to at 4 it is 12, so it is increasing. So I'll draw a graph which is having an increasing gradient. That one shows as if it is 0. I don't want it to be 0 at the origin. Okay, so that will be the graph. The gradient increases because the velocity is increasing. So x should have an increasing gradient against time. Okay, it should not be perfect horizontal at the origin, because horizontal at the origin would mean the initial velocity was 0, yet it was 0.5. The mass of the trolley is 2 kilograms. Show that the component of the weight of the trolley down the slope is 8.3. We have seen that the component of the weight down the slope is mg sine theta. So the component is equal to the component down slope is equal to mg, or the weight, sine of 25, which is equal to m is 2 times 9.81 sine of 25, 2 times 9.81 sine 25, which is 8.29, approximately 8.3 newtons. Calculate the resistive force Fr. So the resultant force, we have seen that the resultant force F resultant is equal to mass times acceleration, which mass is 2, and the acceleration we got as the acceleration was 2.875 or 2.9. 2.875, that was the resultant force. And if it moves, if this is the resultant force is the difference between the component down the plane. The resultant force here is the difference between the component down the plane and the resistive force up the plane. The resistive force is upwards. So let this be the resistive force down the plane. The component down the plane is this one. The difference between the component down the plane and the resultant force is the resistive force is the resultant force. So F resultant is equal to the component of the weight down the plane, W sine 25, minus the resistive force Fr. So we shall say the resultant force is equal to mg sine 25 down the plane minus the resistive force R. So 2 times 2.875 is going to be equal to mg sine 25, we have got as 8.29 minus Fr. So I make Fr the subject, so it will be 8.29 minus 2 times 2.875. So that is 2.54. So Fr is 2.54, approximately 2.5. A ball is thrown from A to B as shown in the figure. If you want, you can resolve velocity in the horizontal, it will be v cos 60, and in the vertical, it will be v sine 60. The ball is thrown with an initial velocity of v at 60 degrees to the horizontal. The variation with the time t of the vertical component of velocity of the ball is shown from t equals 0 to t equals 0.6. Of course, the vertical component reduces to 0. It is moving towards to the maximum height. At maximum height, the velocity in the vertical is 0. Air resistance is negligible. Complete the figure for the time until the ball reaches B. Until the ball reaches B. Let's see. So it comes back, it moves upwards and comes back. Okay. The ball is thrown. Let's see the variation with time t. If it comes back to the same horizontal, it means the time it takes to reach maximum height is the same time it takes to reach to come back. So it takes 0.6 upwards, it will take 0.6 to come back. So I will draw a horizontal line which reaches up to 1.2. I mean, I will prolong the line until we reach 1.2. So let's prolong this line up to 1.2. Okay, so the line goes up to here, somewhere there. Because the negative part of velocity just shows moving in opposite direction. It arrives at point B after 1.2 seconds, because the time it takes to reach maximum height is the same time it takes to fall the same vertical distance downwards. Then calculate the maximum height reached by the ball. So now maximum height reached, since we have the initial velocity, which is, I think this is 5 point. On the vertical, the scale is 2.2 divided by 10, 0.2. So this is going to be 5.9. It is in the middle of the box. So even here, it must have stopped at negative 5.9 here. So the initial velocity is 5.9. So you could also use equations of motion. Okay. But you could also use S is equal to UT plus a half AT squared. They said air resistance is negligible. So this is going to be initial velocity in the vertical initial velocity, I'm considering when we are moving, if it was to move from the vertical, from top down, falling downwards, because the height is going to be the same. I'm considering falling downwards. So if it is falling downwards, it starts from rest in the vertical. So that would be 0 plus a half times 9.81. I will not put a negative because I'm just considering the motion downwards. The time it takes is 0.6 squared to reach the ground, to take the same time. So 0.5 times 9.81, then times 0.6 squared. So that one gives us time of 1.77, or approximately 1.8. Alternatively, somebody may want to use v squared equals to u squared plus 2as, and we want s. At max here now I'm considering it going upwards. At maximum height, v is 0, so 0 squared is equal to initial velocity vertically upwards is 5.9 from the graph, minus, because now I'm considering it moving upwards, so 2 times 9.81 times h. So h is going to be 5.9 squared divided by 2 times 9.81, which gives us the same thing. So h is 1.77. So this is method 2. Calculate the horizontal component Vh of the velocity of the ball at time t equals to 0. So horizontal component Vh. So Vh is equal to V cos of 60 degrees. But we also have that V in the vertical, I'm calling it VV, is equal to V sine 60. But this one has been given. This one has been given as 5.9 from the graph. So I'm going to divide equations. V in the horizontal over 5.9 should be equal to V in the vertical, which is V cos 60 divided by V sine 60. So small v cancels. It means V in the horizontal is going to be 5.9 times cos 60 over sine 60, or it can be 5.9 times tan, or times 1 over tan 60, which is 5.9 divided by tan 60. So it can be 5.9 divided by tan of 60, which is 3.4. Or you can simply say cos 60 divided by sine 60 times 5.9, which gives you the same answer. On the figure 2.2, sketch a variation of VH, that is the horizontal component of velocity. Label this VH. Of course, since there is no force in the horizontal component remains constant at 3.4. So we look for 3.4. 1, 2, 3, 4, 5. That is 3. 3.2. 3.4 is here. So I'll draw a horizontal line at 3.4 up to a time of 1.2. So that will be a horizontal line. They said label this VH. So that is VH. That one is VH. Of course, your graph does not need to go beyond 1.2. 1.2, I think, stops there. Okay. Then the ball has a mass of 0.65. Calculate for the ball the maximum kinetic energy. Of course, maximum kinetic energy is achieved when the speed is maximum. So maximum kinetic energy EK is equal to a half mv squared, which is going to be a half times the mass, which is 0.65, times the maximum speed. Okay, sorry for that. The ball has mass of 0.65. Calculate for the ball its maximum kinetic energy. So for maximum kinetic energy, the ball should be having the maximum speed. What is going to be the maximum speed here? What is going to be the maximum speed here? Okay, so this is going to give us, from here we can see the maximum speed, which is going to be, we are going to find V. I'll find V since we have that 5 in the horizontal, in the vertical we have 5.9 equals to V sine of 60, that is in the vertical. So we can find V. V is going to be equal to 5.9 divided by sine of 60. So 5.9 divided by sine of 60, and this gives us the speed as 6.81. Of course, the ball has maximum speed when it is just leaving or when it is just landing. That is, at this point here, we needed the V. We need the V for the kinetic energy. So V is either use the horizontal component or the vertical component. We'll be able to find V. But the vertical component at t equals to 0 is 5.9 from the graph. That's why I'm now finding V from that. So now I substitute this as 0 as 6 point, that is 6.81, and this should be squared. So this is going to be equal to that answer times 0.65. So that answer should be squared times 0.65 divided by 2, and that is 15.1. So that is 15.1 is the maximum kinetic energy, 15.1. Then the maximum potential energy above the ground, of course, for potential energy, E potential is equal to mg times h, which will be 0.65 times g, which is 9.81, then times h. We saw the maximum height was 1.77 or 1.8. So this is going to be 0.65 times 9.81, then times 1.77. So this gives us 11.3. Okay. An object is moved from point P to point R either by a direct path or by the path P to Q to R, as shown. Okay. P and Q are both at the same level. R is vertically above Q. Explain whether the work done moving the object against the gravitational field is the same. Of course, the gravitational field means the force is vertically downwards. So when you move from P to Q, there is no work done against the gravitational field. Work is only done when you move against gravity. So it means work will be done when it's moving along QR or along PR, but there's no work done against PQ. And the work done against QR is going to be the same as the work done against PQ against the force due to gravity, because the force due to gravity is vertically downwards. It only depends on the gain in height. Therefore, work is equal to, work done is equal to the force times displacement in direction of the force. Remember, the direction of the force is in the vertical. So the displacement considered here is going to be in the vertical. And I'm saying the work done is the same in the vertical direction. Work done is the same in the vertical direction. Work done is the same in the vertical direction as the same distance is moved in the vertical, whether you move along PR or Q or PQR, as the same distance is moved in the direction of the force. The same distance is moved in the direction of the force. That is to say, if I can add more explanation, there is no work done along PQ because it is not moving against gravity. In other words, i.e., no work done along PQ, as there is no displacement in the direction of force. When you move along PQ, you are not doing any work against gravity, so there is no work done along PQ. So the only work done is when you move against gravity. Okay, the ball is thrown with an initial velocity v at an angle theta to the horizontal as shown. You can even resolve horizontally, it would be v cos theta, and vertically it could be v sine theta. The variation with the height h of the ball is shown in the figure. Okay. Use the time to reach maximum height to determine the vertical component Vv of the velocity of the ball. Time to reach maximum height. Let's see. Where is maximum height? I think maximum height is somewhere here. This is maximum height. What is this time? I think this is in the middle, so that's 1.500. The time to reach maximum height is 1.500. And we can even see the maximum height, but let's use V is equal to U plus AT because they want us to use time. At maximum height, V is 0. Initial velocity in the vertical is going to be the component of the velocity in the vertical, which I'm calling VV, minus 9.81, then times the time, which is 1.50. So what is V in the vertical? So V in the vertical is 9.81 times 1.5, which is 14.715, or approximately 15. The horizontal displacement of the ball at t equals 3 is 22.5. At t equals 3, it is 22.25.5. So let me look for 25. On the vertical, each box is 1 meter. 21, 22, 23, 24, 25.5 is in the middle. 1, 2, 3, 4. 1, 2, 3, 4. So 25.5 is in the middle. Draw the variation with the t of the horizontal displacement x of the ball. So how does the horizontal displacement vary? So using s equals to ut plus a half at squared, the acceleration in the horizontal is 0. So it means when t is 0, the horizontal displacement is 0. So the graph starts from the origin. And when t is 3.0, the horizontal displacement is 22.25.5. So that is a straight line. So I'll simply draw a straight line from the origin up to that point. So it is just a straight line between 0, 0 and 3, 25.5. For the ball at maximum height, calculate the ratio potential energy of the ball over kinetic energy of the ball at maximum height. Okay, so we know that at maximum height, at maximum height, at maximum height, of course, the vertical component of velocity becomes 0. It means the only velocity that we have is that in the horizontal. And remember, velocity in the horizontal from s equals ut plus a half at squared. The acceleration in the horizontal is 0. So at maximum height, s in the vertical becomes, at maximum height, velocity in the vertical, vv is going to be 0. Using s is equal to ut plus a half at squared, we only remain with the horizontal velocity. So at maximum height, remember they have told us that the horizontal displacement is 25.5. So 25.5 is equal to initial velocity in the horizontal, which is the horizontal component vh, then times the time, which time is going to be 3. The other part is going to be 0. So it means vh is going to be 25.5 divided by 3. It remains constant anyway. So that is 25.5 divided by 3. That is 8.5. So the velocity at the maximum height in the horizontal is 8.5. In the vertical it is 0. Now we can find, in other words, I'm saying vh remains constant. It remains constant because the acceleration is 0. So the ratio is now the one I want to look at. The ratio is going to be equal to, for potential energy to be mgh, for kinetic energy to be a half mv squared. So m has cancelled. So this will be, the 2 in the denominator goes up, so it will become 2 times g, which is 9.81, times h. H we can get it from the graph, the maximum height we can get from the graph. So this is in the center of this box. So this is 10.2. I think that is 11. It is in the middle, so that is 11. So this will be times 11 divided by, the 2 has gone up, so I just divide by v squared, which v is 8.5 squared. So that will be equal to 2 times 9.81, then times 11 divided by 8.5 squared, which is 2.99. So that is 2.99, or approximately 3.0. That is the ratio. In practice, air resistance is not negligible. Set and explain the effect of air resistance on the time taken for the ball to reach maximum height. Of course, since air resistance is not negligible, the ball will reach maximum height in a short period of time. The air resistance increases the resultant force down. The air resistance, because if the ball is moving upwards, the weight is downwards, the air resistance is also downwards. So it means the resultant force downwards increases, and remember it is in the opposite direction to the motion. So it is giving a greater deceleration from F is equal to ma. The resultant force downwards increases, so the acceleration downwards increases, but it is moving in the opposite direction. So this acceleration is a deceleration. Therefore, we shall say the resultant force equals to the weight plus frictional force. Or air resistance. And this is greater. And it will be greater. So the deceleration is greater. So the deceleration is greater. And if the deceleration is greater for this ball, then it means it will take a small period of time to reach its maximum height. Hence, the time is less. Hence, the time is less. Okay. Figure 2.1 shows an object M on the slope. Okay. M moves up the slope, comes to rest at point Q, and then moves back down the slope to point R. M has a constant acceleration of 3 meters per second down the slope at all times. Whether it is going upwards or it is going downwards, it has a constant acceleration down the slope. This is down the slope at all times. At time t equals to 0, M is at point P and has a velocity 3 meters per second up the slope. The total distance from P to Q and then to R is, in other words, PQ plus Q to R is 6.0 meters. Calculate for the motion of M from P to Q, the time taken, P to Q. So using V equals to U plus AT, because the acceleration is constant. At Q, it comes to rest. That means V is 0. Initial velocity is 3.6 minus, because the acceleration is negative. So that will be minus 3.0. The 3.0 is always down the slope, and yet is moving up the slope. So it means T is equal to 3.6 divided by 3.0. So that is 1.2. That time is 1.2. Then the distance traveled. So we can find the distance using the equations of motion. For instance, we can say S is equal to UT plus a half AT squared. So I will consider it when it is moving from Q. When it is moving from Q back to P, the distance is the same. But from Q, I know velocity there will be 0. When it is coming back, when it is moving downwards. So I will say this implies this will be 0 plus a half times the acceleration, which is 3.0. Down the slope, it is positive. The time we have got it above as 1.2, but this is squared. So this is 0.5 times 3 times 1.2, and that is squared. So this gives us 2.16. That could be method 1. Method 2, you could find the distance to rest from P using the equations of motion, such as V squared is equal to U squared plus 2AS. So here I get 2.16, or I can use V squared equals to U squared plus 2AS. At the highest point at Q, it comes to rest, so that will be 0 squared equals to, initially it is 3.6 squared. It is moving against, because the acceleration is downwards but is moving upwards. So this will be minus 2 times 3.0, then times S. So the distance S is 3.6 squared divided by 6. is it 3.6 squared divided by 6, which is 2.16. Show that the speed of m at r is 4.8 meters per second. So we have seen that p q plus q to r is 6.0 meters, which means qr alone is going to be 6.0 minus, we know pq is 2.16. So this is going to give us the distance qr, 6 minus the answer, that is 3.84. That is qr. Okay, so if now we know the distance, we can use v squared equals to u squared plus 2as. We are starting from q, where initial velocity is 0. Therefore, v squared is going to be 0 squared plus 2 times the acceleration is always 3, then times s, the distance down the slope, which is 3.84. 3.84 times 3 times 2. You get that one. Then you find the square root, which is 4.8. So v is 4.8. Okay. On the figure, draw the variation with the time t of the velocity v of m for the motion from p to q to r, p to q to r. So from p, there is a speed of 3.6. My graph starts with 3.6. 2 divided by 5, that is 0.4. This is 2.4, 2.8, 2.8, 3.2, 3.6 is here. So that is 3.6. Then it becomes 0 at q after a time of 2.1. Is it 2.1? The time is 1.2 when it becomes 0. So on the x-axis, the scale is 0.05. So this is 1.05, 1.1, 1.15, 1.2 is there. So this is 1.2. So that is a straight line. So I first draw that straight line from 3.6. The velocity reduces to 0 at 1.2. At the time of 1.2, the velocity becomes 0. Then the velocity goes up 4.8 after a time of the velocity becomes 4.8. So we have to find the velocity goes up to time of, up to 4.8. That's after what time? That's after what time? Let's check the time. But even if I don't have the time, I know it is a straight line because it's now moving in the opposite direction. I just look for 4.8. So it should take, I think that is up to 3. Where is 4.8? So this is 4.4, 4.8. Those are 2. It's around there. So this is going to be a straight line. Okay, so the line continues as a straight line at 4.2. Okay, so you can draw a better line on your paper with your ruler so that it stops up to 4.2 at around 3 seconds. Okay, so that is the graph. It is a straight line from 3.6 to v equals to 0 at 1.2, and then the line continues up to negative 4.2 because there's a change in direction because it moves to point Q and then it returns in the opposite direction. So there is a change in direction, that's why the velocity is downwards. Okay. Then lastly for this part, the mass of M is 450 grams. Calculate the difference in the kinetic energy of M at P and at R. So difference in kinetic energy will simply be a half M, and difference in the values of velocity, let's say V at P or V at R squared minus V at P squared. So this will be a half times the mass, which is 0.45, that is 450 grams. Velocity at R is 4.8, this is squared. Velocity at P was 3.6, that was squared. So you have 0.5 times 0.45 times 4.8 squared minus 3.6 squared, and that is 2.268, which is approximately 2.3. Okay, so that will mark at the end of part 3, and we wait for the last part, which is part 4. I hope you enjoyed this and have a blessed day. See you in part 4. Bye bye.